10.2, using the fundamental counting principle. In the previous section, in 10.1, we obtained complete list of all possible results for various tasks. However, if the total number of possibilities is all we need to know, then actually listing everything out is unnecessary and can be difficult or tedious to obtain, especially if the list is long. And in the case of using a tree diagram where repetitions were allowed, there were many possibilities. So if I scroll up, we have 27 different possibilities. And it didn't matter what the first digit was. There were always 3 different choices for the second or third digit. That's where the uniformity criterion for multiple part tasks comes into play. What this means is a multiple part task is said to satisfy the uniformity criterion if the number of choices for any particular part is the same no matter which choices are selected for previous parts. So in many cases where uniformity does hold, we can avoid having to construct a tree diagram by using the fundamental counting principle. What is the fundamental counting principle? The fundamental counting principle states if I can spell correctly, that when a task consists of k separate parts and satisfies the uniformity criterion, if the first part can be done in n ways, the second part can be done in n2, and so on until the kth part. Then the total number of ways to complete the task is given by the following product. So n1 times n2 times n3 until we get to the kth part. Now let's do an example of this. How many 2-digit numbers are there in our base 10 system of counting numbers? So we have to figure out the number of ways to get the number of counting numbers in our base 10 system. Now, our first digit is going to be numbers 1 through 9, because remember, we're not going to have a counting number start with 0. We're going to be using from 1 to 2 until we get to 99. So how many different ways are there? First digit is going to be from 1 through 9, which is 9 different ways. And then the second digit is going to be from 0 through 9, which is 10 different ways. And so we get 90 different 2-digit counting numbers. Now, what if we want to find 2-digit numbers with restrictions? And in this case, it would be 2-digit numbers that do not contain repeated digits. That don't contain repetitions. And so we need to select the first digit. And in this case, it's going to be from 1 to 9. So we have 9 different digits. And we have to subtract 1 from the second digit because one non-zero digit has been used and cannot be repeated. So we're going to have 9 different ways for the second digit instead of 10. Which leaves us with 81 two-digit numbers that don't contain repetitions. Let's do another example. How many non-repeating odd 3-digit counting numbers are there? Well, we have our first digit, our second digit, and our third digit. Well, what do we know about odd digits or odd counting numbers? They have to end in an odd number. So from our list of 1 to 9, we have 1, 3, 5, 7, and 9. So we're going to have 5 choices for our third digit because it has to end in a odd number. Well, then we move on to the first digit, which is going to be 1 through 9. However, since we have already used a digit for the third place in this counting number, we're only going to be able to use 8. And for the second digit, we can do 0 to 9, which is 10 digits. But since we have already used 2 and there's no repetitions allowed, we can only use 8. And so we're left with 320 non-repeating odd 3-digit counting numbers. Let's do another example. In some states, auto license plates have contained 3 letters followed by 3 digits. How many such licenses are possible? Well, it doesn't tell us that, it doesn't restrict us to not being able to use repeating digits or repeating letters. So we have 3 letters followed by 3 digits. How many letters are there in the alphabet? 26. Well, this question doesn't tell us that we can't, that it tells us that we could repeat letters, so we could still use 26 for the second letter, and 26 different possible ways for the third letter. And then we move on to the digits. We can use 0 through 9, which is 10 possible ways. And since we can repeat digits, it'll be 10 again for this, 10 again for this. So in total, it'll be 26 to the third times 10 to the third, which gives us this many possible license plates. Let's do another example. A 4-digit number is to be constructed using only digits 1, 2, and 3. So a 4-digit number has to be constructed with 1, 2, and 3. Well, it doesn't give us any restrictions. And when we're asked how many such numbers are possible, we're going to have 3 options for the first digit, 3 options for the second digit, 3 options for the third digit, and 3 options for the fourth digit, which gives us 81 different possible outcomes. Now, we're left with a restriction. What if we want to know how many of these numbers are odd and less than 2,000? Well, if it has to be less than 2,000, there's only one possible digit for the first number, which is 1. Because we can't have 2 or 3, because if we have 2, it'll be greater than 2,000, or if it's 3, it'll be greater than 2,000. Now, what about for the second digit? Well, it doesn't matter. We can have 1, 2, or 3 be in there. And for the third one, it doesn't matter because we can have 1, 2, or 3. Now, for the last one, it says it has to be odd. And the only odd digits out of 1, 2, and 3 are 1 and 3, which gives us 2 possible ways to end this number. And finally, we are left with 18 different possibilities. We now move on to factorials. So the factorial formula is as follows. For any counting number n, the quantity n factorial is defined as follows. So n factorial is going to be equal to n times n minus 1 times n minus 2 times till we get to the end. So for example, if we have 8 factorial, it's going to be 8 times 7 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. If we have 12 factorial, it's going to be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we could do a couple examples. Three factorial is going to be equal to 3 times 2 times 1, which is going to be 6. Six factorial is going to be equal to 6 times 5 times 4 times 3 times 2 times 1, which is going to be equal to 720. If we have 6 minus 3 factorial, it's going to be equal to 3 factorial, which is going to be equal to, as we've seen from A, 6. If we have 6 factorial minus 3 factorial, it's going to be 720 minus 6, so it could be 714. What if we have something like this? 6 factorial over 3 factorial. Now, you may want to do 6 divided by 3, which is equal to 2, but this is wrong. How you would do it is you'd work out the factorial, and then cancel these factorials out. So now you're left with 6 times 5 times 4, and you're going to get 120. What about 6 over 3 factorial? You don't distribute the factorials into the 6 and the 3. You work out the parentheses first. So you're going to be left with 2. And then you get 2 factorial, which is just 2 times 1, which is just 2. And so hopefully you guys get the idea of this, to where we can move on and look at 0 factorial. This is something that you have to remember. The definition of 0 factorial will always be equal to 1. Now we can look at the arrangement of n distinct objects. The total number of ways to arrange n distinct objects is simply n factorial. So for an example would be, if Michelle has 7 essays to include in her English 1A folder, how many different orders can she arrange them? So if she has 7 essays, 7 distinct essays, total number of ways to arrange them will just be 7 factorial, which is going to be 7 times 6 times 5 times 4 times 3 times 2 times 1, which is equal to 5,040. Another example is, say, Trisha is taking 13 preschoolers to the park. How many ways can the children line up in a single file line to board the van? You have 13 distinct children. And you want to see how many ways you can arrange them. So 13 distinct is going to be simply 13 factorial, which is going to be this figure here. Now say some of these objects contain lookalikes. How would that change? Well, if we have n distinct objects, arrangements of n, where one or more consist of lookalikes, then we're given the formula n factorial over n1 factorial times n2 factorial times nk factorial. Let's do an example of this. Determine the number of distinguishable arrangements of the letters in each word. So the first word is attract. Well, we have 1, 2, 3, 4, 5, 6, 7 distinguishable, and we contain 3 t's and 2 a's. So it'll be 3 factorial times 2 factorial, because we have 3 t's and 2 a's. Now, could solve this by doing 7 times 6 times 5 times 4 times 3 factorial. Cancel these out, and you're left with 7 times 6 times 5 times 4 over 2 times 1, which is going to be 420. Well, what about this word, niggling? We have 8 letters total, but we contain a couple of lookalikes. So there's going to be 2 N's, 2 I's, 3 G's. Similar to above, you can solve it as follows. 8 times 7 times 6 times 5 times 4 times 3, 2 times 2 times 3, and we're left with 2 times 1 times 2 times 1 is going to be 4 over 8 times 7 times 6 times 5 times 4, which is going to be 1,680. So that is going to be 10.2.